Hello YouTube, welcome to Logic 102. Last time we talked about the 6 different types of symbols that you can have in mathematics, those being terms, functions, relations, logical connectives, quantors, and then I had a bonus category for dialect, which is all the things that are just unwritten rules about how we write down mathematics. So let me quickly go over all of these. Terms, that was just objects like numbers. You have the number 1, you have the number pi, cubes. A cube can be a term, even a set of... I had the example of all the transformations that keep a triangle the same. So the set of these 3 mirror axes and these 2 rotations, one clockwise, one counterclockwise, and the action of doing nothing. That's also something like a group, which can be a term. It's called D3, if you remember. So these are our objects, and they can be split in variables and constants. Variables are undetermined, constants are given with your theory. Usually variables are things like x, y, z, and constants are the number 2. Sometimes a is used as a constant, or can be anything really. This is why also it's not the case that when you have something that is not just a number, it's automatically a variable. A can be a constant, e can be a constant, pi is a constant, right? So yeah, it's just about whether it's determined, and we'll talk a bit later when we talk about quantors more in depth. So that's terms. And now we can go on to functions. So functions map one or multiple terms to another term. So it can be something like f of x equals x squared. And in this case, this f is the function and it eats one term, and we use brackets next to a function to show what its inputs are. But we don't always write functions like this, and I was maybe not so clear last time, but this is part of the dialect, right? And this was a one-ary function, meaning it takes in one term, and we had the example of a two-ary function being plus, so it takes in 2 terms, gives us 1 new term. Well, there's other functions, like these are all example functions that use numbers as terms, but I haven't given a function that doesn't take a number. A good example is something like a group homeomorphism, for instance, from group theory. But maybe that goes above the expertise of this YouTube audience, so I won't give that example. So last time I made this little meme about with the mediocre woodworking analogy, and I said that functions are kind of like forgotten or not really important, but that's only the case in what I earlier called ZFC, or main branch mathematics, Zermelo-Fraenkel choice, and we'll get into what that means. However, there is different interpretations of main branch mathematics, such as category theory. And in category theory, I don't know too much about it, so don't take this as fact, but I think functions in category theory actually represent what terms represent in ZFC, and they are the important ones, and terms are kind of, I don't know if they are important in category theory, but the roles are reversed there. There were some prominent mathematicians that thought that category theory should be the way that we interpret mathematics. But it turned out that Zermelo-Fraenkel choice was how we understand it now, and that is what I'm teaching now. But as I said earlier, logic is like the beta branch, and who knows what logic will be like in a few years and how we interpret everything then. But in any case, learning this also gives you a better understanding of all those things, so it's not that these are completely separate. On to relations then. Relations, I said, were really the bread and butter. Relations, they give us truth values, so they actually say something about whether a sentence is true and not only about what an object is or how it gets moved around. equals is a relation, and I actually made a little mistake. I said that in my last video I said that the is included in relation was the only relation in set theory. This is a two-ary relation that says whether the left thing is an element of the set on the right. So for instance 2 is an element of the integer numbers. But there's actually a second relation that's axiomatically defined in set theory, and that is the equal sign. And in set theory, two sets are equal if they have the exact same constituents. So 2, 3 is equal to 3, 2 as a set, for instance, because they have the exact same constituents. And that's also an axiom in set theory, I believe. Yeah, these are both two-ary relations. This is a symmetrical two-ary relation. This is an asymmetrical one, because the opposite is not true. I also gave the example of a one-ary relation, like is even, and I didn't have a three-ary relation, but I thought of one, dot, dot, and dot, form Pythagorean triplet. So for instance, 3, 4, and 5 form a Pythagorean triplet, because 3 squared plus 4 squared equals 9 plus 16 equals 25 equals 5 squared. And that's called a Pythagorean triplet. So this would be a three-ary relation. But that's maybe a bit too bulky, so let's get rid of it. Now these first three, I really put a lot of emphasis on the last video, but these last two, the dialect I won't talk about anymore. You just have to infer when something is dialect. I think you learn this by practice. But logical connectives and the quantors, we have a lot to talk about. So logical connectives, I said that there were 16. If you think about all the two-ary logical connectives that are possible, and that's based on their truth table. But I didn't explain what any of those things meant, so let me do that now. So if we imagine we have a sentence A that is either true or false, and we have a sentence B that is also either true or false, then we can connect them with a logical connective, and we can use OR, for example. So this says A or B. And this is a new statement. So we can call this new statement C. If we make a table, we put A here, we put B here, and we put A or B here. And we make a little table. How many possibilities are there for A and B? Well, A can be false, and then B can be false, or A can be true and false and B can be true, and like this and this. So 1 here means true, 0 is false. If both are false, then A or B is also false, but in any other case they are true. So this is called the truth table for this OR statement. If you imagine the truth table as a binary number, then you can see that there are 16 possible truth tables. But 2 of them will result in, of course, just always false or always true, which we call upside down T and T. And they don't need an input, because whether you have an input there or not doesn't matter. So this one would be the one that is 0, 0, 0, 0, and this is 1, 1, 1, 1. And some of them are not so interesting, like 0, 1, 0, 0. What would be the interpretation of this? This would be not A and B, would be this truth table, right? Because if A is false and B is true, then this will be like this. And then we can have some brackets here, but the ordering usually not as before any other logical connective. I said that there are a few more important logical connectives, so let me write all of them down. Earlier we saw AND, OR, let me write down AND, OR, implication, if and only if, not, negation, Sometimes this is if double F, if and only if. I don't know why. This is if single F. So and or if and only if, not. Are there any important ones that I'm missing? Yeah, there's one from computer science that you don't really use in mathematics, and that is the exclusive OR. XOR, let me call it. And that one is an OR, but it's false when both are true. So only one is allowed to be true. So last time I said that the truth table for if is a bit weird. So let me give it. So this, I wrote down if, but you really should read it as if A, then B. So if we write down all our true values, this is true if the implication holds. So if we know A, then B has to be true. If A is true and B is false, then it is not a consequence, so this is false. If A is false and B is false, it gives us no new information, because that's not what this symbol is used for. We don't care about what happens when A is false. But we just return true because we don't want any contingencies. We don't want to write down false statements, right? And the same holds for this one, because we just don't care about what this says when A is false. It's interpreted as assume A is true, then B has to follow from it. So these two we just write down as true because they don't matter so much. It's confusing, but this is the truth table. If you have all of these logical connectives, you can do what's called a truth tree with them. And there's actually multiple different traditions in doing this. And I'm not going to go into any of them, I think, because they are kind of boring, and I don't think you learn a lot from them, but there's some important lessons. Let me go over the important lessons. So a truth tree in the tradition that I learned works like this. If you have an A and you have A implies B, I'm gonna use a single arrow now. Sometimes a single arrow is used, sometimes a double arrow is used. This line means we know this, and then on the next line we're allowed to conclude B. And you read it as logical steps. And this is one of the rules. This is called the modus ponens. It's also called implication elimination. In other words, we eliminate the implication arrow. And every connective has their own rules associated with them. You should be able to understand it. So you read the first line, we know A implies B, so we can conclude B has to be true. So really here we combine two statements and we synthesize them into one new statement. You can look up all the rules for all the connectives. I would say the most important one is the proof by contradiction, or reductio ad absurdum if you're pretentious. So this one goes like this. If we assume A is true, and these brackets mean assume, and we do some steps, this can be anything. We can add some other whole tree in here if we want to. And we conclude that something is not true, we can conclude not A. And at this point, we can eliminate our assumption. This is the most important part in a proof tree. A proof is done when all assumptions are eliminated. So sometimes we do a little stripe across the assumption. So there's no assumptions allowed to be in here anymore. And then we can conclude that not A is true. So how does this look in practice? Let me do a quick proof by contradiction. One more thing about proof trees. If a collection of statements, let's call it fancy T for theorem, if it proves another statement A, then we write down this sideways T to say there is a proof tree leading from a collection of sentences that concludes in A. As modus ponens says that if we have the collection A and we have the statement A implies B, then this can create a proof tree that leads to B. But don't get too caught up in this notation, it's not so important. Let me do a proof by contradiction, and this will be your first proof, which is very exciting if you've never done a proof before. The proof has two parts, and it's a classic proof. First we have to do a lemma. A lemma means a small subproof that we use for the full proof. Our lemma is n squared is even if and only if n is even. So let's write down n and n squared. Make a little table so we get a good feel of it. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So intuitively this feels like it's true, right? If 1 is odd, so its square is odd, 2 is even and its square is even. So the proof for this I'm going to skim over because this is not a proof that I want to build up to. But the idea is that we have to first prove prime number factorization. So n can always be written as a collection or and I'm going to use some fancy mathematical notation. If you don't know this, just ignore it. N is the multiple of some prime numbers pi to the power mi, where mi is the multiplicity of the prime number pi, and then if n is even, n even implies that m2 is larger than or equal to 1. And we know that when we square a number, its prime factorization is going to be 2mi, with the same mi's as here. And then for the proof from left to right, we sometimes write a little. First you prove it from left to right if you want to prove an if and only if. This is a lesson 1 about proofs. If you want to prove an if and only if, first do left to right, then do right to left, or the other way around, doesn't matter. So we first do left to right, and we write a little bracket. This is very much a dialect thing, right? I just did a whole bunch of rambling, but it's easier to first do right to left in this proof. So I edited out all my rambling. We're doing right to left. N is even implies n squared is even. So if n is even, we know that its prime factorization looks like this, with m2 is larger or equal 1. This is actually... Okay, I'm sorry, I made this so confusing. This should be m1, because 2 is the first prime number. So p1 is 2. P is all the prime numbers. So p1 is 2, p2 is 3, p4 3 is 5, p4 is going to be 7, and you just go down the list of the prime numbers. And that's how you do prime factorization. And then if m is 0, if m1 is 0, that means there is no division of 2 in the number n, and that means that our number is odd. But if m1 is 1, that means our number is even. So we know n is even, that's what the right hand says, and we want to prove n squared is even. So we want to prove m1 times 2 is larger than 1. So if we see that 2 is larger than 1, we're already done, and this one is done. Sometimes you see a little square when a proof is done. And then the other way around, we start with the assumption that n squared is even, and we want to know that n is even. Well, if n squared is even, and n is a natural number here, if n squared is even, that means that all its prime factorizations have a multiplicity that is also even, including m1. So m1 is going to be some positive number. Let's call it, so m1 for our n squared is going to be some 2 times some other integer m prime, let's call it. And m prime is going to be larger than 1 because n squared is even. And if we divide this by 2, we also find that the multiplicity of 2 in our number n is going to be larger than 1. In other words, it is even. And this is a lot of difficult fancy words, and I hope I didn't confuse you too much, but this is the way that proofs go. You kind of get to, you have to get used to, especially when you are just learning proofs, you have to get used to throwing so many things under the rug because you just can't go into every nitty-gritty detail. But we have proved our lemma. Hopefully you agree with me. So let me put a little box here. And now I want to get on to the real proof that I wanted to show, because we wanted to do a proof by contradiction. And our next proof is actually an interesting historical proof, and that is, we want to know if the square root of n can be written as a fraction a over b, where a and b are natural numbers. And sometimes we write a little double T when we want to prove something before the sentence. So this is like a question mark. I would prefer just writing a question mark after. That's more colloquial language. I also don't know if I'm using the double T correctly, so I'm just going to use the question mark. So is the square root of 2 written, can we write the square root of 2 as a fraction of 2 natural numbers? And a fraction of 2 natural numbers is also called a quotient, and we have a little symbol for it. It's a fancy Q. First thing we do is we can square both sides, right? So we have the square root of 2 and then we square it, and that's going to be equal to 2, and this will have to be equal to a squared over b squared. Okay, we have this part, and we can rearrange that, and that implies b squared times 2 equals a squared. In other words, oh, I forgot to say one thing. Quotients can always be simplified. So, for instance, 6 over 3 is equal to 2 over 1, right? Because both are divisible by 3, which is just 2. And I want to know if a and b, every quotient has a unique simplification. So I also want this to be the unique simplification, which means a and b cannot be divisible by the same number. Everyone on board? A squared is an even number, because we have 2 times something that's going to be even. And we use our lemma to conclude a is even. A is even. So we can write a as 2 times a prime, where a prime is a divided by 2. We just get the even factor out of there, and a prime is again a natural number. So then here we find b squared 2 equals 2a prime squared. And then we can simplify b squared 2 equals 4a prime squared. And then we can divide both sides by 2. And then we find b squared equals 2a prime squared. And now we see that b squared is also an even number. So this implies b, using our lemma again, b is even. Okay. So we've concluded that a is even and b is even. So both can be divided by 2. But our initial quotient had to be the unique simplification. So it already had gone rid of all the common divisors. And that is a contradiction. And when we find a contradiction, we often write this little lightning thingy. We can write down what the contradiction is. we can write 2 divides A, 2 divides B, and A and B have no common divisors. And so this concludes the proof that that the square root of 2 is not a quotient. So we write not square root of 2 quotient. Now a tiny thing about relations. When we have not relation, you are always allowed to write the relation with a little dash through it. So not an element of the quotients. And we have proved that, so we can make a little square. And that is how you do a proof in mathematics. Now I did it very haphazardly. It's very difficult to do a proof where you're very collected and really go through all the steps very neatly. It's doable. I don't have the patience for it. I don't think you have to be able to do this to be a good mathematician. Some people disagree though, but I know so many mathematicians who just do their proofs by hand waving all the time. It's good to be able to have some patience with it, but I hope you enjoyed this proof and that you, if it's the first proof you've ever seen, this is... I will, maybe when we have some more knowledge in the future, I will do some more proofs that are a bit more elegant in their in how I display them. But I wanted to have people who don't know a lot about this be able to read it. I think I failed in that. This was more difficult than I expected. But yeah, and that was a proof by contradiction. So that's how I started this whole shebang. Let me explain this again. Our assumption was a over b equals the square root of 2. And a over b is a general quotient here. So we can write a over b is an element of the quotients. In other words, square root of 2 is an element of the quotients. This is called a substitution, where if you have an equal sign and you have one thing on the side of the equal sign, and you can substitute it with the other thing on the other side of the equal sign. So our assumption is really this. This is our assumption. And then we did some stuff. We proved the lemma first, and we did some other things. And we eventually concluded that we got a contradiction. We said that a and b was divisible by 2, and they were in their unique irreducible form. So they are not allowed to be divided by the same number. And thus we concluded not our assumption. So square root of 2, not an element of the quotients. Because this was our assumption, and we conclude the negation of it, and then we lift our assumption. We're not allowed to use this anymore as a statement, and we have proven the negation of the assumption by contradiction. Okay, that was a lot, so take a little bit of time to take it in maybe. The takeaways here are, in the last lesson I said whenever you write down a sentence in mathematics, it's assumed to be true. There is, however, this counterexample. A statement is allowed to be false if you have a running assumption, because then you are working in this kind of bubble where you are working under this assumption, and as long as you can eventually lift the assumption by, for instance, the proof of contradiction, you get to live in the realm of truth again, basically. But in this little intersection here, you can have false statements. There is, annoyingly, again, an epistemological distinction here, and that is between the constructivists and the formalists. It's called the Hilbert-Brouwer controversy in the history, basically. So Hilbert was a guy that I talked about last video also, and he laid a lot of the foundations of how we do mathematics, because he was just a prolific teacher at the time, and he knew a lot of different courses, and he talked with a lot of different mathematicians, and he kind of collected everyone together to say, hey, let's formalize all of mathematics into one field. And Brouwer was one of the more religious types that I was talking about last video, who believed that the mathematical logic is sort of a reflection of the cognitive structure of the universe or something like that. And he didn't believe in the proof of contradiction. There's still other assumptions that you can make, I think. Yes, if you're making an or statement, but I don't know how or statements work in constructivist logic. If you say A or B. So this was the general rule for the negation, if you remember. I also gave the general rule for the this is also called not introduction, because you introduce a not sign. This is not a rule, this is an application. But I want to show the rule for or elimination. If you know A or B is true, and you assume A and you derive C, you assume B and you derive C. These are two different proof trees, but both A and B, when you assume them, derive C, and you know that either A or B is true, then C is true, and you can eliminate both the assumptions A and B. Intuitively, you should understand what this means. This means you know A or B is true. So you branch out, you think about, what if A is true? Can we conclude C? Yes, then we're happy. Then we think, what if B is true? Can we then also conclude C? And then we find yes in this case, and we're also happy. And then we say, why does it do that? That's not what we say. Then we say, okay, well, in either case, C is true. So C has to be true in either case, if we know one of them has to be true. And we can conclude with that. And we can also keep having this statement because we derived it independently, because this is also a different truth tree. So this thing really has 3 truth trees, right? But on this line, you bring all of them together to conclude C. That is the rule. And this is one of the rules. It's called being able to draw. It's called or elimination. Okay. And every logical connective and every quantor has their own rule for elimination and their own rule for introduction. So that are truth trees. I didn't say one thing about truth trees. And yeah, I'm still talking about logical connectives here, but I did a little aside about proofs. That was a bit big, probably. But one thing that we hadn't talked about pertaining logical connectives is tautologies. A tautology is a statement that is always true. Let me give you an example. Given we are not constructivists, not A or A. This is called the law of the excluded middle, and it says that every statement is either true or false. And this is within first order logic, which is what we're working towards. This is a tautology. It's always true. And how do you know it's a tautology? Well, you can build a truth tree that uses all our rules that we have constructed. I don't like this example so much, so I might use a different tautology to show you how to prove tautologies. let's go with A implies A. This seems like a very stupid tautology. It just says if A is true, then A is true. The modus ponens actually says that if you assume A and you do some proving, you find out B, then you can say that A implies B, and you can remove the assumption. So we can use the modus ponens to prove this very easily, this tautology. So let's assume A. Then that means that A is true because we've assumed that it to be true. And that means we can use the modus ponens here on A itself. And we find A implies A. And here I use the single arrow. I already said I use them interchangeably. And this is a completed proof tree. So this was a rule. This is axiomatically true, but this is an actual proof. This is arrow introduction. Okay, that's proof trees. I won't go into the other version of proof trees because there's already a YouTube video on it. And they go into how to branch, how to prove a statement is true. Yeah, proof trees, no one uses them in practice except intuitively. And this comes back to what I said last video about the difference between practical main branch mathematics and logic. So in my opinion, they're a bit useless. But this is also called proposition logic, and it's what a lot of logic courses start with. So that concludes our section about logical connectives. So I want to say one more thing actually about the if and only if, because really this is the most powerful statement in mathematics. If you can prove that A if and only if B, then these two statements are the exact same. And that is incredibly powerful, because wherever you find the one statement, you can just substitute it for the other statement. And I want to give one example. This is very abstract. It pertains to linear algebra. It says that the statement L is a bijective linear transformation. And what that means is quite difficult, but there are some rules for it. For instance, L takes in a vector x and it maps it to some other vector y. And it has a few rules. For instance, L lambda x, if you multiply the vector with a scalar, it has to multiply y with a scalar. And this means that it preserves angles. You can watch 3 Blue 1 Brown's video about linear algebra to understand this. But this says something about linear transformations that are bijective. And there is a statement within linear algebra, one of the most important ones, and that says that the determinant of the matrix representation of L is not equal to 0. And this is an if and only if statement. Don't worry if this all goes over your head, but this top statement says something very general about linear transformations. And this bottom statement says something extremely computable. This is just an algorithm. You can find what the determinant of this thing is. So this if and only if statement kind of bridges the gap between something general, theoretical, and something computable, practical. And it says that they are the exact same statements. The left-hand side is the exact same statement as the right-hand side. Every time you find a matrix with determinant not 0, you know it's a bijective linear transformation. And that is extremely powerful. And all of mathematics, a lot of mathematics is devoted to showing that two things are the same statement. This is why this arrow thing it's super important. I can give some other examples, but I think you get the gist. By the way, bijective in the terms of linear transformations means it doesn't squish any dimensions into one. So the dimension of the input space is the same as the output space. But it also means that you can reverse the function. So that's the if and only if thingy. Another thing about logical connectives I earlier said that if you say A implies B, that it's the same as doing a line break. So first writing down A, then writing down B. And you use this on your exams all the time. If you say x squared is equal to 2, therefore x is the square root of 2, or x is minus the square root of 2. Oh, that's a big square root, minus the square root of 2. And you use this on your exams, right? You have your paper here, and these are 2 lines. And you might be solving some quadratic equation that goes like so. And you want to find these zeros. This is what you write down on your answer sheet. So exercise 1, find the zeros of this formula. Maybe you started with x squared minus 2 is 0. So x squared minus 2 is this graph, and then you find the zeros. It should be familiar with you, and what you're secretly doing is every line break there's an implication. But we don't write that down. But these things here are statements that we saw in the last video, if you remember. These are variables, which are terms, and this is a function and another function and a term and a relation. And the relations give you true values, and these A and these B, they represent these true values. Do we have time for quantors? Or should I leave that to the next video? I think I will leave it to the next video. So I'll leave it at this, and I'll see you then. Bye bye. I forgot to do checking for comprehension. So here I have some exercises. And let me get rid of my face here. I'll give you 5 seconds to pause the video and you can look at these. So the first one says which logical connective fits the following truth tables. So you have to find the connective that fits the truth table. Just think about the connectives that you've seen and which one of these fit. And then the second question is which of the following truth tables is complete. In other words, forms a correct tautology at the end. And yeah, I'll leave you to think about it. I will give you the answer in 5, 4, 3, 2, 1. Okay. So the first one here says it is true only when A and B have the same true value. So that is the if and only if. And it is false if they have a different one. The second question here, it's the exclusive OR from computer programming. It's true when either one is true, but not if both are true. The next one is the negation. It's a very simple truth table. It's just the opposite of the value that you had. And that it's a one-ary thing was kind of a hint that it had to be the negation. This is a correct proof. It uses the modus ponens. So if A and B are true, then A is true in particular. That's what that says. And then this next one, it's an open thing because this assumption here wasn't closed. Also, this sentence doesn't make sense. A implies A and not B. How does A tell you anything about B? It doesn't. So this is not true. And then this last one is actually quite interesting. So let me just enhance it a bit. So this is called De Morgan's law, or at least it is one of the implications in one of the multiple De Morgan's laws. The opposite implication also holds, but that's a whole different truth tree. I use this, I start with 3 assumptions, and here I use the OR introduction. So if I know that A is true, A or B is in particular true. And I also use this assumption twice. I put it here, and this tree is symmetrical, as you can see. Here I do the exact same thing with B, and then A or B again. And so both of these say some expression, A or B, and not the exact same expression. So that is in contradiction with the law of excluded middle. This statement has to be true or false, but it can't be both. So this is a contradiction, and we can use this contradiction to remove one of our assumptions. And this is a weird thing about truth tables. You can kind of choose which assumption you remove. But if I remove this one, my proof would be a dead end and I wouldn't be able to use it here anymore. So I remove this A, and here I remove the B. I didn't put the stripes here because that would make the exercise too obvious, but you don't have to. This 2 means it is revoked, the assumption. And now I conclude that I have A and B, so I can write down A and B. Sorry, not A and not B. So I can write down not A and not B. And then I can use the modus ponens again with my last open assumption. So I know that this thing here implies this thing there. And you can actually do the implication the other way around with another truth table. If you like this, you can look up the rules for truth tables. Actually, let me put them on the screen real quickly. Here is all the rules for truth trees. So you can repeat things. You can, this is the reductio ad absurdum, or the proof by contradiction. The modus ponens, the elimination of the arrow, introduction of the arrow. Oh, so I was right at the start. The elimination is called the modus ponens. Okay, it doesn't matter what. So the introduction of the arrow is the thing where you remove the assumption. And then this is the elimination of the negative. So you can say that the proposition implies false if it is the negation of the proposition. And you can introduce the negative like that also. Elimination of or, of and. So if A and B is true, A is true in particular, and you can do that vice versa. Introduction of and. Elimination of or. Yeah, this is a different way of saying it. I used it with assumptions, but you can use the introduction of the arrow twice to get this version of the rule. What do we have here? The introduction of, so elimination of or, introduction of or. These are all the basic rules, and these are sort of axiomatically true. We just say, this is how these rules work, deal with it. And that's how you define what or is and is in mathematics. Okay, so here we are back at our table. As an extra homework exercise, you can try to prove the reverse of this statement. So this implies that. And then you have completely proven this logical law. And it's how you kind of switch between or and. But we will see more of this in the next video. So that was it. Goodbye.